Good morning and welcome everyone. Thank you for attending today's sessions for the School of Mechanical and Electrical Engineering Technology at Sheridan College. We are pleased to be a sponsor of National Engineering Month this year. And today's session is about the Conceive, Design, Implement, and Operate framework that we adopted in our 2 Bachelor of Engineering degrees at Sheridan College, the Bachelor of Engineering in Mechanical and Bachelor of Engineering in Electrical. The CDIU framework emphasizes on the importance of experiential learning, open-ended problem solving, and teamwork. So through the CDIU framework, students solidify deeper knowledge of engineering fundamentals and develop system thinking skills. I must also mention the importance of integrated learning, which is a key feature of the CDIU program, where students learn personal, interpersonal, and system building skills together with disciplinary knowledge in the context of professional engineering. It is also important to mention that the instructional method used within the CDIU framework has less emphasis on the passive transmission of information and more emphasis on stimulating students' critical thinking, and equally important on applying and analyzing and evaluating ideas. So today's sessions is going to be done by 2 of our panelists. The first panel will be conducted by Dr. Amin Gubiti and Dr. Louis Mononga, and they will be talking about the Conceive, Design, Implement, Operate, and how this was embedded within our engineering degree. And then the second panel will be taking this a little bit further and walk us through the importance of graduates from accredited degree programs to get the license and the designation of professional engineering. So with that, I would like to hand it over to my colleagues. But before we hand it over, I need to go over the land acknowledgement statement that we are here. Let me just, okay, so I would like to recognize the territories that we are holding this virtual event on. We would like to acknowledge that all of Sheridan's campuses reside on land that has been and still is the traditional territory of several indigenous nations, including the Anishinaabe, the Haudenosaunee Confederacy, the Wendat, the Métis, and the Mississaugas of the Credit First Nation. Since time immemorial, numerous indigenous nations and indigenous peoples have lived and passed through this territory. We recognize this territory is covered by the Dish and One Spoon Treaty and the Two-Row One Palm Treaty, which emphasize the importance of joint stewardship, peace, and respectful relationships. As you may be joining us from different territories, we acknowledge that the many diverse nations and territories you are joining from. Sheridan College affirms it is our collective responsibility to honor and respect those who have gone before us, those who are here, and those who have yet to come. We are grateful for the opportunity to be learning, working, and living on this land. With that, I would like to hand it over to my colleagues, Dr. Amin Gubiti and Dr. Louis Monanga, for the first session on the Conceive, Design, Implement, Operate framework within our engineering degree at Sheridan College. Thank you.
Good morning, everyone. So can everyone see the screen?
Yes, we can.
Okay. So as it was mentioned by Dr. Amjad Majid, the first presentation is on project-based learning based on the CDIU concept. I'm joined here by Dr. Louis Monenga. We are jointly coordinating the Bachelor of Mechanical Engineering program at Sheridan College. So here is basically an overview of what we will be talking at the first part of the panel. I'll give you an overview of the Bachelor of Mechanical Engineering degree program, and we'll talk about what is CDIO, what is that based on that concept that we have adopted in developing the Bachelor of Engineering program. I will very briefly talk about what is CAB and how that would align with CDIO, and my colleagues at the second part of the panel will basically elaborate on that and how the experiential learning that we'll be talking in the first part of the panel is aligned with the CAB accreditation. We'll give some ideas about the BUS project or integrated learning aspect of the CDIO concept, and also some of the other experiential learning aspects of the program. And for those of the participant attending, they may be interested in knowing about the admission, different ways of admission to the program. So now I pass it on to my colleague, Dr. Luis Manga.
Hello, everyone. I've already been introduced. So this part of the presentation, I just want to mention that the degree in mechanical engineering, as well as the degree in electrical engineering, both of them are designed in such a way that students will have hands-on experience throughout the degree, and that experience will be had through projects. So essentially, it's a project-based undergraduate degree. And in mechanical engineering, we have two specializations. One is mechatronics. The next one is energy. So those are the two specializations. Now, the feature of this degree is that we take advantage of college education, which is very practical, and integrate it with university education, which is traditionally theoretical. So the students will be taught the theory at university level. In addition, they are going to have hands-on experience. So in essence, we are exposing our students to the best of both worlds. I'll pass it to Dr. Amin. Oh, sorry, I will still continue. So how is the program arranged? So it's a 4-year degree program. The first 2 years are based on foundational mathematics, natural sciences, and engineering sciences, similar to what you would find at universities. And after the first 2 years, students will be expected to go through a mandatory 4 months work term. So every one of our students will have to take this work term. So it's similar to co-op, but we call it internship. So when they come back from the 4 months work term, they will have the opportunity to choose between the two specializations, mechatronics or energy. So then they go into year 3. So year 3, they are going to take common courses and specialization courses. After 3rd year, they have optional work terms. These are 2 terms. So they can take 1 term after term 6, or they can take, actually they can take 1 term after term 6, and they can take another term at the end of term 8. So once they have all the 3 4 months work terms, they can qualify for a co-op certificate. So as you can see, the program is basically exposing our students to projects from year 1 up to year 4, and it culminates with a final capstone project.
So here is a overview of the program map. For the first 2 years, in mechanical engineering degree program is very similar, in fact, with the mechanical engineering degree programs in universities, with the exception of wherever we have the opportunity to add a project or lab components or other hands-on activities we have included in all the courses. We also have breadth courses that would cover the complementary studies requirements of the Canadian Engineering Accreditation Board. The second, the year 3 and 4 would include courses that would cover the specialization in mechatronics as well as energy systems. In year 4, the students have two courses that are focused on the capstone. The first course will be basically conceive and design, which are the first two elements of the CDIU. Then following that, in the last term, they will cover design, implement, and operate, which are the 3 elements of the CDIU. So this was just give you an overview of the program map. So what is CDIU? CDIU was an initiative that is started by a number of universities, including MIT, and they looked at concepts to include activities that are sort of interconnected and include some of the professional skills, such as teamwork and communication, and most importantly, they would include experiential learning into the education, into the engineering education. So it also includes, and it's very important, a quality assurance process, a continuous improvement that is certainly aligned with the CAB and Canadian Engineering Accreditation Board requirements. So in the development of our program, we actually followed the CDIU concept, and we have included integrated learning and experiential learning as basically concepts that we have followed. In terms of the CAB, for those of you who are not familiar with CAB is the accreditation body in Canada, and it basically would ensure the education requirements of the graduates of engineering programs, so that it's ensured that the quality and the curriculum are based on some standards. So bus project is basically an integrated learning where a project is shared between multiple courses. Project is based multiple courses. In each year, we have 2 or 3 courses that would cover a bus project, that would share a project, and that would ensure that the multidisciplinary project with different aspects, including some of the professional skills, teamwork, communication, they are all sort of included in the assessment of projects and the assessment of students. So here is an example of a project that the students have done in the year 1, where they have shared between the engineering design and problem solving, and also physics 2, where they have looked at different aspects of the project, and they have actually built a prototype, they have simulated, and they have provided the drawings for what they have designed. So here is another example that my colleague would actually explain.
I mean, can we go a slide up?
Oh, okay, sorry.
Yeah. So for year 2, we have another bus project, which involves 2 courses. The first course, which is the main course, is fluid mechanics. And the second course is instrumentation and measurements. So in fluid mechanics, basically, the project involved hydronic piping system design. Now, in year 2, students are are exposed to concepts like Bernoulli's equation, and that is extended to the general energy equation, where students learn to calculate losses in piping systems. And then based on those losses, they should be able to size the pump. And starting with a project, they should be able to draw a 3D model and then select the pump to satisfy the flow requirements. In the second part of the project, students look at measurement, pressure measurement, velocity measurement, flow measurement, viscosity measurement, and temperature measurements. So they use the knowledge which they acquire from instrumentation and measurements to carry out those different measurement methods.
Okay, so as I mentioned, we include in our program a lot of different experiential learning components, and wherever we have the opportunity, we include some experiential learning components such as labs and projects. Actually, let me mute this. So here I'm showing a steam turbine that we have in our lab where it's fully instrumented, and it's actually a complete cycle where we have a boiler, we have a boiler, we have a steam turbine, we have a cooling tower, and what we see here is basically a recording of the measurements that are done. So students get that experiential learning exposure in a course such as thermodynamics, where traditionally in universities universities don't really have such complete labs on such theoretical courses. So the students do energy and mass balance in their classroom, and then when they actually see the components and they do the calculations, that would actually basically enforce their learning. So we also it's actually you, Louis. So
yeah. So the next part of the program is experiential learning through labs, and of course you have talked about projects. So the school has got state-of-the-art labs. For instance, here you can see robotics lab, and also instrumentation, automation lab. And also there, at the bottom left, you have electro-hydraulic lab. So through these facilities, students are able to perform their lab work, laboratory work, and also project work. And the next lab is thermofluids lab. You can see top left, that is a wind tunnel that is used for fluid dynamics experiments like boundary layer measurements. You can also perform drag and lift experiments. Bottom left, and that that equipment is used for different types of flow measurements. You can use orifice plates, you can use venturi to perform the measurement, even rotometer. In the middle, at the bottom, you have Pelton wheel, which goes together with bottom right. The bottom right is the base unit, which is used for characteristic variables of turbo machines. We can connect, it has a centrifugal pump that runs, and you can connect Francis turbine, Pelton turbine, and be able to analyze the different characteristics of turbo machines.
So being in a college system, we actually have the advantage of having so many lab equipments that we can easily integrate into our Bachelor of Mechanical Engineering program. In our energy lab, we have a range of equipment, including a geothermal learning system that includes, in addition to what we use it for at the diploma level for maintenance and control of HVAC system. In our degree program, we learn about the thermodynamic cycle of the geothermal systems. It's actually equipped with industry standard components and it's a full size, a 2 refrigeration ton heat pump. So students get that exposure with equipment that are actually used in industry and in the actual development of components. It has variable speed air blower. So it's not really usual that you see such equipment in a degree program that is not based on a focus with a focus on experiential learning. So students use these equipments. Here in the middle, I'm showing a hydrogen fuel cell. We are in fact the only college in Canada that has a full hydrogen fuel cell with that would simulate a hybrid energy system. It's a fairly advanced hybrid energy system with battery, hybridizing a hydrogen fuel cell with batteries. In our top right, I'm showing a refrigeration cycle where students see an older style capillary tube as a throttling device and all kinds of different aspects of a thermodynamic cycle of a refrigeration cycle. That's what we basically see in our refrigerators and air conditionings in the home. So when the students see the equipment, in addition to the theoretical components that they cover in the courses, they actually get a much better understanding. And we all sort of learn differently. Some of the students appreciate this experiential learning quite a lot. We also have a range of solar systems in our energy labs. We have a solar thermal system. We actually have two different designs of solar thermal systems. We have solar evacuated tubes, and we also have a flat plate collector. We also have a solar photovoltaic system, a 4 kilowatt solar photovoltaic system that is part of a microgrid, and it's hybridized with batteries. So in terms of, these are obviously industry level components. They are not little trainers or kits. So students do actually get exposure to advanced energy systems as well. So all in all, the point is we are in a sort of advantage of including equipment and lab experiences that are usually part of a diploma and advanced diploma level, but we have upgraded that to include that in our Bachelor of Engineering degree programs.
Okay, the last part of the presentation has to do with admissions. Now, I would like to preface this by saying that it is Ministry's policy, Ministry of Education policy, to provide pathways to students at every level. So here at the college, we have diploma programs, which are 2-year programs and 3-year programs. So students who take 2-year programs can transition to 3-year programs. So that is a pathway. So here, through this program, Bachelor of Engineering in Mechanical Engineering, we are also providing a pathway for students who have a 3-year advanced diploma to be able to join the degree program. So how are they able to do that? So these are the requirements. We expect the students to have completed the 3-year advanced diploma in mechanical engineering or closely related program. And they should have a GPA minimum 70%. Now, what we have realized that if we say GPA of 3.0, the way the GPA is defined can differ from college to college. So that's why we say 70%, because that is universal. And then through the 3-year diploma, the student must have taken 2 calculus courses. Here at Sheridan, we have differential calculus and integral calculus. And then we also insist that they should have a minimum of 60% in core courses in 3rd year of their advanced diploma, because these are courses which are, I would say, which would give us an indication that the students will be able to survive in the degree program. So typically in mechanical, this will be like fluid mechanics, thermodynamics, machine design, dynamics of machines, so typical courses. And admission, this is very important from a CAB point of view. Admission is always done on a case-by-case basis, so it's not a blanket admission system. So once the students qualify, then they are admitted through the bridging semester. So in the bridging semester, they are going to take about 8 courses, and these courses are based on 1st and 2nd year of our bachelor's degree program. So once they successfully complete those courses, they can then join the degree program in year 3, semester 5. And then in addition, before graduating, they will have to take also, I mean, this is optional. They may decide to take a co-op and get a co-op certificate. So that is how we provide the pathway for students coming through the diploma system.
Okay, so that sort of wraps up our presentation. If there is any question, we'll be more than happy to take on the question, or we can move on to the.
Actually, before we open the floor to questions, Dr. Majid, our Associate Dean, has a few comments I'd like to make.
Yeah. Thank you, John, and thank you, Dr. Amin and Dr. Lewis. That was very informative. Really enjoyed this session. What I really wanted to add is just to go back to the CDIO framework. And what the CDIO brings is adding an experiential learning to the degree of the student throughout, from year 1 all the way to year 4. It is important that we remember that the CDIO brings what we call bus projects, and that's something alluded to my colleagues too. So the bus project starts from year 1. And if you had a chance to look at the program map in year 1, you will see, for example, if we take 3 courses, physics, mechanics, exploring engineering, as well as linear algebra. Now, students within the CDIO framework will be able to link what they study in these 3 courses in what we call bus projects. So, for example, if we take some students in our programs are studying, for example, the robotics arm. So if we take the robotics arm as a bus project within the CDIO framework in year 1, the students will better understand the physics, the forces that they are studying in physics, for example, and how these are applied in a robotics arm at the joints, for example. And in order to, for example, to solve these set of equations, we are studying linear algebra, so that's where linear algebra comes into play. Exploring engineering, students will better understand the role of engineers within and what they produce and the services they do for the society. So they link what they study in these 3 courses into an end result, a project. This way, they will better understand what they are learning in the lecture and how this is applied in real life world. Now, the scope of the bus project within the CDIO becomes a little bit bigger as they move to year 2 and then year 3. when they get to year 4, students will be very well prepared, not only with the technical skills, but most importantly, the soft skills that the industry needs in terms of communications, teamwork, presentations, and so on. And that will allow them to even expand the capstone project to a more of a research-based project. So with that, I would like to now open it up to questions to my colleagues. Thank you.
Okay. And if anyone does any questions, I'll give a few minutes, please, to either ask them in the chat box or just identify your spin. I'll call on you. In the meantime, I do want to bring up a comment that I thought was very interesting by Matthew Hamilton, who's a civil engineer, and was very surprised how much crossover there's between disciplines. The specific example Matt brought forward was some of the piping related mechanical work compared to civil hydraulics. And that's something I do find very interesting is as we think of our discipline as very siloed, there is a great deal of crossover.
I certainly agree that there is a lot of overlap, and most of the engineering projects are truly very multidisciplinary, and there is a lot of connection between mechanical engineering, civil engineering, and obviously in mechatronics, that is one of our specialties between electrical engineering and mechanical engineering. So yes, definitely. And civil engineering is something that we probably look into in years later on and include it as part of our Bachelor of Engineering programs.
Okay, it didn't seem as though anyone from the audience had brought forward any questions at the time. With that being the case, I think we'll move forward to the next panel session and hopefully able to engage in a little robust discussion afterwards.
Thank you, John. So let me start sharing my presentation. Good morning, everyone. My name is Human Abovati, and I am a professor of electrical engineering at Sheridan College. Dr. Berg and myself are program coordinator of our new Bachelor of Engineering Electrical Engineering program that we started in fall 2020. So the topic of this panel is how we prepare BEng graduates to be career and licensure ready. I will start off with a very quick presentation, and after that, I would like to have a discussion and question and answer and discuss this further. My colleague, Dr. Gobeti and Dr. Mununga and Dr. Majid mentioned BOSS project. So I would like to start off with the BOSS project again, and then I will connect this experiential learning experience to the CAB graduate attributes and the requirement of accreditation in an engineering program. So as my colleague mentioned, a BOSS project is a project-based learning activity that is shared between 3 courses in winter semesters of year 1, year 2, and year 3. Although there is no limitation that we can extend it to fall semesters, but currently the structure that we have happens in winter semesters. So students apply knowledge and skills that they obtain from different fields of studies or different courses, rather, to complete the deliverables of one project, one single project. And we have chosen the contributing courses to cover different aspects of competency and knowledge that is required to complete that project. Something that is always a matter of question that how we would evaluate that project. Each project has multiple deliverables, and these deliverables are being evaluated in the contributing courses by the professor who teach the courses. So I have 3 examples here about the BOSS projects that are happening, or we are planning to implement them because we are currently in year 2 of the program in Bachelor of Engineering Electrical Engineering program. The first project is a wind turbine that our first year students work on this project, and you see the contributing courses here are identified. Engineering design and problem solving is the course that the students learn the mechanical aspects of the design. For example, how to design the blades, how to design the assembly, how to design the structure of the wind turbine. And then there is another course that is Fundamental of Physics 2. More than half of that course is on electrical and magnetism. So the related topic to a wind turbine in that course might be the definition of electric current, electric voltage, measurement of these parameters, and how to calculate the power, the output power of a wind turbine. And also the structure of generator is basically based on electromagnetic induction. So students apply the knowledge that they are gaining in physics 2 to explain and describe the principle of operation of a generator. The third course can be either communication, technical communication, or computer programming. If it is a computer programming, the student's contribution to that project, or this course contribution to that project rather, would be have to analyze, have to write a code and analyze that process, or do any kind of optimization. It's going to be a coding practice. And if it is a technical communication, for sure it covers the skills, the technical communication skills, including report writing or presentation skills. Another example that is currently happening for the first time, so unfortunately I don't have any sample to share, is year 2 projects. So we are currently working on that project. Students are currently working on that project, and we are supervising and leading the projects. And the contributing courses this time are 3 courses in electrical engineering from 3 different fields, important fields in electrical engineering. We have Electronic Circuits 2, that is an analog electronic course that covers amplifiers, comparators, DC to DC, not DC to DC converter, multivibrators, oscillators, PLLs, and so. And the other course is a microprocessor system. That's an introductory course to microprocessor. And the third one is Signals and Systems 1. So how do these courses align with a filter design or implementation of a filter? So students start in Signal and Systems 1, and they explore different configuration, different transfer functions of filter in that course. They do analysis, they do simulation, and they explore different transfer functions. For example, what's the difference between a Butterworth filter and Chebyshev filter? Or what's the role of filter order in the frequency response? Or what's the meaning of cutoff frequency or roll-off rate? And then the output of this course, that is actually a transfer function, goes to Electronic Circuits 2. And in Electronic Circuits 2, students start with a transfer function in frequency domain, in Laplace domain, or f of s, and then they design a filter using electronic component like op-amps. And then they design a PCB as well, and they implement that filter on a PCB with proper ports for the input, output, power supply, everything, and they do the analog implementation phase of the project. And then another output of Signal and System that goes to the third course, that is microprocessor systems, is the transfer function in Z domain, or f of z. And then in microprocessor systems, students learn how they can implement the same filter, but with a digital system. So these 3 courses work together, and the learning that the students obtain in different courses are being used to achieve same deliverables, actually deliverables of one project. And the third project that we are planning to do it next year, it's a BOSS project in third year of the program, and this is on motor controllers. The contributing courses are again electric machines that students achieve engineering knowledge that is required to do that. In this course, students learn different aspects of electric motors and also the control and the control procedures for the electric motor, including stepper motors and servo motors. And then in control system, they learn about the control theory in time domain, in frequency domain, and a little bit digital control. And design of digital system is all about VHD programming and a bit PLC, programmable logic controller. So they learn concepts of the concepts of electric motors in electric machines. They learn concepts of control systems in control systems, and then they use the third course, that is design of digital system, to implement a digital controller for the motor. So again, this is another example of how three courses collaborate toward the deliverables, toward achieving deliverables of one project. So this BOSS project CDIU concept that my colleagues explain, and the experiential learning options that our students have. So how do we use these options, and why do we need this for the program accreditation? I'm trying to connect the concept that is discussed so far to the program accreditation. So we all know that many of our students after graduation and after having the other requirements might be interested to become a PEng, to get a license as a professional engineer and work as a professional engineer. So one of the requirements, the academic requirement for this process is the students should be graduated from an accredited program by CAB, by Canadian Engineering Accreditation Board. To achieve that and to apply for accreditation, we need to show that our students and the program is meeting some criteria. And I have listed these criteria here. I'm just going to read over them, but I'm going to emphasize on one of them, and I will connect the BOSS project and experiential learning and CDIU to that specific one that I'm selecting here. And the first one is the one that I'm selecting. We have a concept of graduate attributes that have been defined by Canadian Engineering Accreditation Board, or CAB. We have 12 very comprehensive criteria to evaluate the programs. I will try to show how they can connect the experiential learning to graduate attributes. But the other aspects of the accreditation, or other criteria for accreditation that have been listed here, are the process of continual improvements, the students' admission, promotion, graduation, academic advisement, and degree audition, the curriculum content and improvement that we should show that the program includes enough content on mathematics, natural sciences, engineering science, engineering design, and complementary studies, and program environment, including students, faculty, support staff, administration, labs, libraries, computing facilities, counseling, and guidance. So let's continue with one of them only, and that is graduate attribute. So if I go to the next slide, here I have the list of graduate attributes, and we have 12 graduate attributes that have been defined by Canadian Engineering Accreditation Board. Let me read over that, and you see that I have highlighted a couple of them here. And the ones that have been highlighted is basically primary graduate attributes that can be addressed in BOSS projects. Although we can find the connection between other graduate attributes with the BOSS project as well, but this is just the primary analysis of the process, and just to give you an idea about the process. So the first one is knowledge base for engineering. That includes competency in math, natural sciences, fundamental of engineering, and specialized engineering. And then problem analysis, investigation, design is one of the most important one. Use of engineering tools, and by engineering tools, my understanding is we include not only lab instruments, but also simulation tools or engineering resources in general. Individual and teamwork, impact of engineering on society and environment, communication skills, professionalism, ethics and equity, economics and project management, and lifelong learning. I think that we can find a very strong correlation between the BOSS project and knowledge base for engineering, problem analysis, design, use of engineering tools, individual and teamwork, communication skills, and economics and project management. To give you an example, again, because this is just the start of conversation and we don't want to really go to details, I'm going to pick one of them, and I will try to make a connection between one of the BOSS project and one of the graduate attributes. And the graduate attributes that I'm selecting is the fourth one, that is design. And I would like to make a connection between our second year BOSS project that was about filters and design. So to do so, I need to include another, actually bring up another concept in this process that we call it indicators. So you see the process on the screen, and let me start with the last one, the right one. That is that's the one that we are familiar with, and they are graduate attributes. And one of the graduate attributes that we are discussing here is design. So these are standards for all engineering programs in Canada, and they are so comprehensive that they are not easily measurable. And they define students' overall achievements. So they are very comprehensive, and it is difficult. They are very difficult to be measured. Now let me go to the beginning. And at the beginning, we have the learning outcomes. So the learning outcomes are defined at the course level. And at Sheridan College, we have the course outlines and learning outcomes that are associated to that course publicly available. So these learning outcomes have been defined in each course. They have been linked to the learning activities, like, for example, labs, like project, like case studies, like exams, and they are measurable. Actually, this is our job to teach them and then evaluate them. So the learning outcomes are something that are defined at the course level, and graduate attributes are at the program level. So we need to have a link between these two, and we call the links indicators. We define the indicators at program level. That means we have defined them for the electrical engineering degree program at Sheridan College, and they are measurable. So the process is, if we have a link between learning outcomes of a course and indicators, and then indicators are pointing to graduate attributes, that means the learning outcome goes toward measurement of graduate attributes. That is our purpose. That is what we wanted to show. I think the next example is going to explain the process a little bit better. As I mentioned, I'm going to try to make a connection between second year BOSS project and graduate attributes. And the graduate attribute that I'm selecting here is the design. So you see that the last step at the bottom is the graduate attribute that we have selected, and that is design. But do we have a learning outcome in that course that addresses the BOSS project? We have a few in electronic circuits too, and I've chosen one of them that is the most relevant one. And the learning outcomes reads, design active filters to realize a described frequency response. So they get the frequency response from another course that was Signal and Systems 1, if you remember, and then they implement that filter. So suppose that they are getting that T of S over there, it's a second order filter, and they need to come up with a circuit like the next one. It includes only one op-amp. There is no limitation for the complexity of that. And they need to design that circuit to implement that. Is it the only option to implement that transfer function? For sure, no. Depends on the transfer function. They might have multiple solutions for that. So it's an open-ended question. And they choose a circuit and they design the circuit. That means they determine the components that are required to implement that transfer function. So here's the learning outcome. And then the graduate attribute that I have is design. So we need to have a connection between these two. And the connection is provided by the indicators that we have for design. So you see that at the middle link, we have DE4 and DE5. So DE for sure stands for design, and why 4 and 5? Because we have multiple indicators for each grad attribute. And for design, I believe we have 5 graduate attribute, 5 indicators for design. And then D1, D2, D3, D4, and D5. And we identified that DE4 and DE5 are more relevant to that project, specifically that project. So D4 is develop a refined design to implement an engineering project. So I think that explains itself. So they have the transfer function, and then they need to investigate, they need to explore multiple options, and then come up with a refined design solution to address that requirement. And the requirement was implementing a transfer function. And D5 is evaluate the performance of an engineering design. This is a very important step of the project. So at the end of this semester, we would expect our students to submit a report on their BOSS project. And this report does not only include the design procedure, simulation result, measurement results. It should be also addressing the performance or evaluation of performance of the system. So have they achieved the design requirements? If they have not, if not, what are the process? How they can improve the design? How they can modify that? What was the cause? And these 2 indicators will be addressed in this project. And as I mentioned, the indicators at one side are connected to the learning outcome, and the other side, they are pointing to one grad attribute. And we do this process for all the grad attributes that are related to that course or mapped to that course. And then we should have the same process for evaluating students' activity to address one of the requirements about the graduate attribute for the program accreditation and meet that criteria for the program accreditation. Thank you very much for listening to this presentation, and I would be happy to continue this conversation now.
Okay, and once again, I will first thank my colleague, Dr. Nova, for his presentation, but invite any questions or discussion from the audience. Dr. Noble-Body, one of the things you very rightly focused on design because it's a critical aspect of engineering education. Are there graduate attributes that are very well suited to be evaluated through BUS projects that don't necessarily translate well to traditional learning activities?
Thank you very much, Dr. Berg. That's a great question, and I appreciate that you brought it up. And absolutely, the answer is yes, and that is the most critical part of my job as a professor, as an educator, because many aspects of our students' activities, like analysis or even design or knowledge base, they can be addressed, they can be evaluated using traditional evaluations like examinations. But the other aspects of the students' work, like for example, teamwork or students' individual work or engineering ethics, these are more difficult to be evaluated. And in this process, one thing that we are working on, and we have the initial draft of that, and we are basically using that currently, is a concept that we call it common skills rubric. So it is a rubric that is defined at the program level, and it is designed to evaluate the indicators. Regardless of the content of that activity, it is pointing to indicators. And the people who are evaluating the activity, mostly they are professors, they are faculty members who are teaching the course, who are marking the students' activity, but sometimes it might be even peer review by the other students. This is basically very general overview of the processing of other grad attribute that cannot be evaluated thoroughly using examinations, let's say.
Okay, so we're talking about what a lot of people in the industry would traditionally call soft skills, things like leadership, teamwork, project management, organization.
Absolutely, absolutely. And these are very well related to the activities that our students working on a project or case study or even lab assignments. The term that I normally use for these activities are performance-based evaluations. That means it is not only the content that they are delivering, it's related to the performance and the methodology and the process that they take to achieve that. That includes soft skills that you mentioned, Dr. Brick, as well.
Okay. Question from Orlando Lambda, and I do apologize if I mispronounced last name, Orlando. What are the admission criteria for the electrical engineering program? And I'm going to give Dr. Navalbadi a second to hesitate there. He's going to pull open the admission criteria on the website.
Absolutely, yeah.
So that he doesn't make a mistake reciting. And it is on the fairly standard. What the published admission criteria is it's that fairly standard high school course package, some math, physics, chemistry, and a minimum grade. And Dr. Navalbadi is hopefully looking as I speak and fill it in. Go ahead, please.
Absolutely, Dr. Brick, thank you. It's English grade 12, is either physics or chemistry, grade 12, U level. Although completing both physics and chemistry are recommended. Mathematics grade 12, including advanced function and calculus and vector, MHF for you and MCV for you, plus 2 additional grade 12 credits at the U or M level. And a minimum 70% overall average is required and minimum 70% in each of the math courses.
Okay. I do want to bring up yes, admission criteria is currently listed as physics or chemistry. We are waiting for ministerial consent to change that admission basis to physics and chemistry. We've been tracking student progress throughout the program, and we found students who do not carry both of those courses are at much higher risk of having a successful outcome from year one. Now, and that is the direct from high school admission basis. That does not reflect the reality of all of our entrants. We have students who are coming for post-secondary education. We have students who are what we might consider to be adult learners who are coming with some career experience. And our admissions department is fairly flexible in working to find equivalencies to this high school admission basis if it is necessary and appropriate.
Maybe while we wait for some questions, I can also elaborate a little bit more about our two streams that we offer in both electrical degree and mechanical degree. I know my colleagues have discussed a number of our labs in the energy stream and the equipment that we have, but I'd also like to emphasize that we do have state-of-the-art equipments in the mechatronics stream as well. And as you can all see, our lab manager, Dan, who is now sitting and live streaming from the robotics and automation lab at Sheridan College. So we do have a number of automation and robotics labs and partner with key industry partners such as FANUC Robotics as well as ABB Robotics. And as you can see, these are all industry standards robotics that we have in our labs at Davis campus in Sheridan. And with that, the students learn with industry standard equipment and technology that gives them competitive advantage when they graduate and enter the workforce. And the CDIO framework is very much correlated to the state-of-the-art equipment that you have. So in that case, it really works hand in hand with the equipment we have, as well as the resources, human resources. All our faculty, as you can see here, have both wealth of experience in both academia and industry. And with that, they were able to bring a number of industrial projects and research projects that allow students to be further exposed to the industrial life applications. And that has helped them a lot. And the standard feedback that we receive from industry, students are very well equipped with the skill sets needed when they graduate. The other point I'd like to also mention that the CDIO framework, as well as our curriculum and labs, are always in enhancement and improvements based on the feedback that we receive from our industry partners. So we do have, for every program, applies the same for the electrical degree and the mechanical degree. We have what we call PAC committee, Program Advisory Council, and that committee consists of representatives from industry partners in GTA, and we meet and we go over all what we have in our labs. They go over the curriculum. They give us feedback from our students that have been on work placement, internship, or co-op, and with that we have always maintained current with our curriculum as well as equipment. So this is what I really wanted to emphasize, and we will welcome anyone who would like to come for a tour to our labs anytime. Please feel free to email us and we will arrange for a tour to our labs at Davis campus for both the energy labs and the mechatronics labs, and we will be happy to do that. We'll coordinate this with my colleagues and our lab manager, Daniel Van Kooten. So are there any questions, John?
There don't seem to be any questions. I'm going to leave my contact information in the chat box. If anyone has anything after the meeting, I can either answer your question directly or put you in touch with someone who can. In the meantime, Dr. Majid, I think it might be appropriate for you to wrap up the session.
Okay, I think, yeah, we'll give it a bit more time for anyone who has further questions. Okay, I think no more questions. Well, I would like to thank everyone for attending today. We hope that you have enjoyed the session as much as we have, and really appreciate your time and your attending today. We would also like to thank our partners here, as you see on this slide, and also special thanks to the Ontario Society of Professional Engineers for organizing the National Engineering Month this year. Lastly, a very special thank you to all our, again, NEM partners and to the NEM team for their efforts and time in organizing and coordinating all these sessions. Very much appreciated. And once again, we hope you enjoyed our sessions. And I also like to thank my colleagues who have worked hard in preparing this session and for their time today. Thank you so much and have a wonderful day, everyone. Thank you.